¿Está prendido el micrófono?
This is my thumb. Oh, it's very large. So that's 2 fingers. That's what he's told to do. That's one of the small.
Many people in the room will be aware that the United States is having an election now. And
I don't think you should go there.
And it brings to mind a almost 300-year-old saying of Samuel Johnson that patriotism is the last refuge of a scoundrel. Now, in our field, it can be viewed that magnetic fields are the last refuge of a scoundrel in this case being a theoretician. So no one has done as much as Tom Troland on magnetic fields, and therefore to try to make honest scientists of theoreticians. And with that, Tom, let's hear the latest.
Thank you very much, Bob. I'm glad to know I'm not a scoundrel. We've already heard, of course, that CMB researchers are scoundrels. I'm glad I don't fall into that same category. It's a pleasure to be here at this meeting, which honors the lifetime achievements of Gary Ferland, although not actually all the lifetime achievements because, well, Gary's not dead. And what that means is there'll be many more lifetime achievements to come from him in the future. It's also a pleasure to be here in Mexico. It's a beautiful country, and Mexico, of course, is on the forefront of modern astrophysics. I first met Gary in 1980. Both of us were hired at the University of Kentucky. And I remember shortly after I arrived at the University of Kentucky, one of the senior colleagues there said to me about Gary, said, you know, that's a guy who publishes like crazy, and he collaborates with everybody. That was then, and it's still true today. Gary was a very promising researcher in his early career at the University of Kentucky, and that promise has been richly realized, as we all know, as time has gone on. So it's a pleasure. It's always been a pleasure to have Gary at my institution, at our institution, to have him on the faculty of the University of Kentucky. And with those thoughts in mind, it's altogether fitting and proper that I should talk today about a subject for which Gary has made major contributions, as he has for so many, namely the question of the role of the magnetic field in PDRs. And in giving a talk that has something to do with H2 regions, it's also altogether fitting and proper to begin with this picture, which Bob Odell showed us earlier, which is his picture. Bob is, of course, very well known for his scientific studies of the Orion Nebula, but I think it's also worth pointing out that Bob is in some sense the Ansel Adams of the Orion Nebula. Some of you may know Ansel Adams was an American photographer of the early and mid 20th century who richly detailed in photographs the beauty of nature in the American West, and Bob has done the same thing with the Orion Nebula. So this picture is familiar to all of you, and it's really not only a work of science, but in my opinion, it's a great work of art. Okay, let me begin then with some discussion of how you would measure magnetic fields in PDRs. This is done through the radio frequency Zeeman effect, which allows us to measure magnetic field strengths of PDRs that lie in front of galactic H2 regions. or as some call them, H plus regions. The Zeeman effect can be detected in the 21 centimeter line of H1 and also in the 18 centimeter wavelength lines of OH. And I'll explain to you in some detail how that's done. Here's a very, very simplified vision, of course, of an H2 region. And if you imagine the radio frequency radiation coming out of such a region, the radiation coming out of the H2 region, of course, is just the radio free continuum, nearly constant in intensity as a function of frequency over a relatively narrow band. But the radiation that's emerging from the atomic hydrogen region has impressed upon it a absorption line seen against the radio free continuum at 21 centimeters. And radiation that emerges from the molecular gas has now an OH 18 centimeter absorption line impressed upon it. Actually, there are 4 such lines, but we'll just pretend that there's just one. This is not a very realistic looking H2 region PDR. Here's a somewhat better example from the work of, Will and his wife, Jane Arthur, and others. But it's the same basic concept where radiation from the free continuum is absorbed by spectral lines in the atomic and molecular gas. And it is those spectral lines that allow us to measure magnetic field strengths. Now, if we take this scenario that you see here and we add a magnetic field, the lines change a little bit. So we go from this to this. If you look carefully, you see the lines now are split. That's the Zeeman effect, which of course is related to the magnetic field. And the splitting that you see is a small fraction of the line width. As a matter of fact, in practice, the splitting that we observe with radio telescopes is a much smaller fraction of the line width than you would see here. It's usually, the splitting is usually about 1% or so of the line width. And that makes a big difference in what we can do. Here you see the same concept in somewhat greater detail. In order to observe the Zeeman effect in radio frequency spectral lines in this limit of very small splitting, which is the limit in which we almost always are. In order to do that, what we have to do is observe the lines separately in right circular polarization, RCP, and left circular polarization. And then the splitting is related to the line of sight component of the magnetic field. And the way in which we detect the splitting is we take the difference between right and left circular polarization. That's called Stokes parameter V. And that difference has a shape that looks like the derivative of the line profile. And the amplitude of that derivative profile in the Stokes parameter V is directly related to the splitting, delta Fz, and therefore related to the strength of the magnetic field through a Zeeman factor shown right here, 2.8 hertz per microgauss for 21 centimeter H1. The numbers are slightly different for other transitions. So in short, we can use separate observations of a radio frequency spectral line in left and right circular polarizations, subtracting one from the other to create Stokes parameter V, to determine the line of sight component of the magnetic field. It's important to recognize that we are only detecting one component of the magnetic field. That's a limitation. It's an unavoidable limitation of this technique. But the basic point is that we measure magnetic fields through Stokes parameter V. And you might think that Stokes parameter V is just a concept of interest to a very few in this audience that has no connection to our everyday life, but in fact it does. And let me explain to you how. Just a few weeks ago, my wife and I went to see a movie, Ghostbusters 2. And it turns out, if you go to see a 3D movie, which is what this movie is, that 3D movie is all about Stokes parameter V. The way they create the 3D effect is to provide you with glasses which pass opposite senses of circular polarization, left-hand circular and right-hand circular. That's how they separate the two images. And so when you see that monster kind of jumping out of the screen and practically landing in your lap, it's all Stokes parameter V. So I was thinking, I brought what I would call a zoomometer. I brought this pair of glasses that I used at the movie, and I put them on, and I was thinking tonight I'd go out and look up and see if I could see the magnetic field in 3 dimensions. Now, you may think that's not possible, but I do remember years ago when I was an undergraduate astronomy colleague who I don't think ever went on into the field. He told me one night he'd gone out and looked up in the sky on a dark night and had seen the stars in 3D and without the glasses. The trick was he had taken LSD before he did it. So I don't know how that works. We'll see tonight if just the glasses alone allow me to see the magnetic field in 3 dimensions? Probably not, but it's worth a try. Okay. Now, this technique of the radio frequency Zeeman effect can be applied with single dish radio telescopes, but it also can be used with the VLA. The VLA provides much higher spatial resolution. And so what we can do, in effect, is make maps of the line of sight magnetic field strength across the face of the source. And Nick showed such a map of the line of sight magnetic field in the veil across the Orion Nebula. I'll show you another version of that. The basic idea is that if you imagine this area now, each of these squares is a little pixel that we can separately image with the VLA. At each pixel, like say that one right here, we see the spectral line in right and left circular polarization split. We take the difference, we get this, and from that we measure the magnetic field there, the line of sight component, do the same thing here for all of them. And the net effect, of course, is to produce a map of the line of sight magnetic field. Here is a spectrum which is similar in some senses to one that Nick showed. This is not an optical depth profile. This is an H1 absorption profile. It could be converted to an optical depth profile, but here you see the absorption line. The same 2 components, component A and B, are seen in this spectrum that Nick talked about in his very nice talk earlier today. So we can observe absorption lines like this. This particular absorption line is for the pixel towards the trapezium, but there are many other pixels that we can independently measure with the VLA data. And here is now the Stokes parameter V spectrum shown in histogram format. And you can see that the Stokes parameter V profile looks a bit like the derivative of the Stokes I. This is one side of the derivative component B, and you see that there. This is component A, and you see that there. We're actually able to detect the magnetic field separately and independently in the 2 velocity components. It so happens that they have similar values, not that you can read them or it matters, but minus 47 microgauss, minus 52 microgauss. These 2 components, which are physically very close to each other, as Nick mentioned earlier, also, as it happens in this direction at least, have very similar magnetic field strengths. So let me show you an example. This is really the same thing that Nick showed, but slightly differently rendered. Here is the famous picture of the Orion Nebula. And so I'll overlay upon this the map of the line of sight components of the magnetic field, and that's shown right here. This is now a map of the line of sight component of the magnetic field for the component A here. And let me show you the map on a slightly larger scale so you can see it somewhat better. Here, these are actually lined up, so you can blink from one to the other. But let me go to a slightly larger version of it. And here you can see from the scale here, these colors right here represent magnetic fields of 50 to 75 microgauss. Across most of the veil, the magnetic field is 50 to 75 microgauss. Up here in this deeply obscured region called the northeast dark lane, the field strengths become much higher. But much of what Nick was talking about and much of what we often think of as the veil really is the region that's shown right here where the field strength is 50 to 75 microgauss. Another region where this same technique has been applied is M17. And here you see now a beautiful optical image of M17. It's a very extensive H2 region, as you know, and it's powered by a half dozen or maybe more O stars, plenty of B stars to go along with it. Here you see a rectangle which shows the region I'm about to show you. These are all lined up, although I should point out first, look at this little region down here. Obscuration is actually part of a large molecular cloud. It's right there. Let's go now to this picture here. And this is now in the infrared false color. You can also see in this case now a part of that molecular cloud, which is mostly off to the side here. This is what's known as M7. This is known as, as the northern bar of M17. This is the southern bar of M17. Now we move to another rendition of M17. The contours represent the 21 centimeter radio continuum emission, which of course is a indication of the true distribution of ionized gas unaffected by extinction in any way. The colors represent H alpha. You see a lot of light here. You don't see so much light down here. So what that tells us that M17 northern bar is rather unobscured, whereas the southern bar is much more obscured. Here you see in green, sort of hard to see, but this now represents part of the M17 southwest molecular cloud. And the interesting thing about this region is that right along here is a PDR, is an interface between the ionized gas and the molecular gas, which is seen almost edge on. So it's a different geometry from the PDR of the Orion veil, which is seen almost face-on. So the 21 centimeter Zeeman effect and the 18 centimeter O-weight Zeeman effect was observed with the VLA some years ago by myself and my former student Crystal Brogan, and that resulted in a map of magnetic field strengths along this PDR right here. So let me show you that map just out of interest. Not so colorful perhaps, but it presents the proper information nonetheless. You can see now these darkened regions. These are regions of high magnetic field, strictly speaking, high magnetic fields along the line of sight. And the field scale here goes up to some 600 microgauss. So there really are some very strong magnetic fields right along this region here, which is the PDR, the interface between the ionized region of M17 south bar and the M17 southwest molecular cloud that is not shown in this picture. Here is just out of curiosity on the same scale. These are all on the same scale. This shows now the O stars that were identified by Hansen et al. And those are the stars that are predominantly powering the H2 region. So this is a classic example of a PDR, which has been studied in some detail, in many wavelengths, of course, this intersection, this interface between the M17 south bar and the M17 southwest molecular cloud. Now, this led to some work that is really at its heart the idea of Gary Ferland, and was published in 2007 by Eric Pellegrini, a graduate student at that time, and others. They presented a cloudy model in which they modeled the PDR between the H2 region and M17 southwest molecular cloud. They modeled that PDR with cloudy, of course, and included the effects of magnetic fields. And they wound up with a model in which the PDR is magnetically dominated. The pressure in the PDR is dominated by magnetic pressure. They assumed that the PDR was compressed by a combination of absorbed radiation, UV radiation from the ionizing stars, and also the pressure of hot X-ray emitting gas in the cavity around the stars. And they found then that the magnetic field strength was increased as the as the PDR was compressed. That, of course, increased the magnetic field strength and increased the magnetic pressure, resulting in a situation where the magnetic pressure then was able to sustain the PDR against the pressure of the stellar radiation field and the X-ray emitting gas. And here is now a rather idealized picture of how this can be imagined. You see here at the top, describe this as before PDR compression. You imagine magnetic fields. The magnetic fields are shown here by these vertical arrows. The concept does not require that the magnetic field be perpendicular to the or parallel, I should say, to the interface regions. It does not require this particular geometry, but that's what I've shown here to make it simple. If the radiation pressure from the stars and from the gas, to such the extent that it exists, compresses things, then that will, of course, not only increase the gas density, but also increase the field strength. That then increases the field pressure, and then this equilibrium is reached between the magnetic field pressure pushing back and the stellar radiation pushing forward, so to speak, as well as the pressure of the X-ray emitting gas. Now, what they found, as I say, is that magnetic pressure dominates the overall pressure in the PDR. And the fact that magnetic pressure dominated in the model means that thermal pressure was largely insignificant. And since thermal pressure in the model was insignificant, that required that the model have low density. However, the thickness of the PDR model depends upon a column density required to extinguish the molecular dissociating radiation. And so the net effect of this magnetically dominated model is that the volume densities are much lower than would be the case in a non-magnetic model, but the thickness is much greater. So it's really a fundamentally different physical characteristic, physical properties of a magnetically dominated magnetic field. Magnetically dominated, all magnetic fields are dominated magnetically, but anyway, magnetically dominated PDR. Let me get this right. Give me a sec. Throw me a frickin' bone here. Anyway, here, I won't spend too much time on these, but here are two models that were part of that paper, and they illustrate this point that I just mentioned about the thickness and the density of these magnetically dominated PDRs. You see a higher field model at the top and a lower field model at the bottom. The colors are encoded in the same way as in earlier slides. Blue is ionized hydrogen and green is the atomic and red the molecular. Over here, you see the pressure, different pressure components. This is the cumulative pressure of the absorbed stellar radiation. This is the pressure of the magnetic field, which is the dominant pressure. Thermal pressure in the neutral region just becomes almost zero. It's insignificant. Now, if you look over here, you see this is now a representation of the density of the different hydrogen components. So this obviously is the H+ region, followed by the atomic and molecular regions. You can compare the model at the top, the higher field model, with the model at the bottom, and you can see that for the higher field model, the width of the atomic hydrogen region, which is sort of what I mean in this context by the PDR, that width is much greater in the higher magnetic field model than it is in the lower magnetic field model. And in the no magnetic field model, not shown here, the PDR is even narrower and the densities are even higher. So this is a very interesting result, and it's based on a fully self-consistent cloudy model, which incorporates magnetic effects. And the significance of this model is that it produces a very different physical regime from non-magnetic models. So non-magnetic models may, if the magnetic field is not properly included, may predict densities that are too high and thicknesses of the PDRs that are too small. And that, of course, has ramifications if you're trying to understand radiation from density-sensitive tracers. Now, the time is, yes. The cloudy model, a fully self-consistent cloudy model, was useful and important in demonstrating at least the physical plausibility of this type of concept of a magnetically dominated PDR in the vicinities of H2 regions. However, in the absence of such a model, we can estimate, crudely at least, using simple principles, the equilibrium field that would be required in the PDR to resist the effects of stellar radiation absorbed and the hot X-ray emitting gas. And so it's a very simple calculation. This is actually done also in the Pellegrini et al. 2007 paper, but let me just briefly mention how this works. We can equate the magnetic pressure in the PDR to the combined pressure of the starlight plus the X-ray emitting gas. Magnetic pressure is simply B squared over 8 pi, and radiation pressure is the flux divided by C. I've separately indicated here the EUV and the FUV, and this, of course, is the pressure that is supplied by the hot X-ray emitting gas, if such exists. So we can then take that next step further. The EUV flux is simply the Q of H, we all know what that is, times the average photon energy divided by 4 pi RIF squared. RIF is the distance between the stars and the illuminated face of the H2 region. That's a very important parameter. And I've also separately indicated the FUV flux as being equal to beta times the EUV flux. And the value of beta obviously depends upon the stellar SED. For the SED that Nick used for his most recent paper that he described earlier today, the ratio is roughly 2.7. Actually, the FUV flux is higher by more than a factor of 2 than the EUV flux, and both, of course, are relevant to this overall picture. So we can put these ideas together into a very simple equation based on these simple principles that allows us to estimate the equilibrium field that would be necessary in the PDR to resist the radiation plus hot gas pressure. And so this is the answer. I know Gary's very much into equations, and so I wanted to emphasize that in this slide. You know, some people play fantasy football. Gary plays fantasy equations. He makes up equations. Anyway, this is the equation, and this is all in CGS units. So it allows us to determine, at least roughly, what the equilibrium field should be. So we can see if this idea works in other H+ regions. We know it works in M17, but does it work, for example, in Orion? Let's find out.
Can I say where that was?
Sorry?
That is the mid-ocean ridge, the Atlantic Ocean.
Gary always wanted to stand on the mid-Atlantic ridge. I told him years ago, if you're going to do that, you're likely to be a kilometer or 2 below the ocean surface, so it's not a good place to be. So he found out a place recently called Iceland where you can stand on the mid-Atlantic ridge, right?
And on the left is the North American plate at that hill.
So there you have it, okay. So here's North American plate. I don't know, is the European plate sort of...
Ridge, European
Okay. Okay, that's a good place for people with split personalities. You can almost stand on two plates at once. Not to say that Gary has one. Sorry?
At 2 centimeters.
2 centimeters per year. So if you were to stand there like this, I guess after 3 years, after a while, you'd have a problem. I wouldn't recommend that. I would not recommend that. Okay, let's apply this idea. Let's apply this idea to the Orion Veil, our favorite place, many people's favorite place to live. We can apply this relationship to the Orion Veil. We know Q of H, as Nick pointed out this morning, we know very well many physical parameters that are associated with the Orion Veil. So this is a good place to try to see if this idea works. It does, of course. Why would I be telling you otherwise? In any case, we know Q of H. We know the distance between the trapezium stars and the illuminated face of the veil. As Nick pointed out, we know something about the X-ray emission from that region, and this number 2.7 I mentioned earlier is known from the SED that has been constructed for the trapezium stars. Plug those numbers into the equation, I'll call it the Troland equation. How about that? Let's call it the Troland equation. That's what this is. Now, henceforth, will be known as the Troland equation. In any case, when we plug the numbers into the Troland equation, we get a field of 70 microgauss, which is very similar to the line of sight fields that are mentioned that are measured, I should say, in the veil, as I mentioned earlier. So what we can say is that this concept of a magnetically dominant PDR works, quote unquote, in M17, and it works in Orion. That is to say, the magnetic fields in both cases that you would expect, given this assumption of equilibrium. The magnetic fields that you would expect and calculate from the Troland equation are similar to, in both cases, the magnetic fields actually measured with the Zeeman effect in H1, 21 centimeters, or OH, 18 centimeters. So that works fine, but what about other H plus regions? So let's take a look there. In the remaining time we have, it turns out over the years, similar types of observations of the Zeeman effect towards H plus regions have been made for 7 other H2 regions. And so we know something about the magnetic field strengths, not only in the Orion Veil, as we've said earlier, and not only in M17, but also in 7 other H plus regions in the galaxy for which this VLA H1 or OH Zeeman effect technique has been applied. So we should be able to calculate the equilibrium values, that is to say, BEQ, and we can then compare them with the line of sight values to see if this idea is more generally applicable, not just to M17 and Orion, but to others. Principal uncertainties is we often don't know Q of H for these other H2 regions because in many cases they are heavily obscured, and so we don't see the stars directly. We can't do a stellar census. Also, the value that you calculate for the equilibrium field in the PDR is quite sensitive to the distance you take, RIF, as you see right here, the distance between the stars and the illuminated face. And that's very difficult to estimate. That value, RIF, is well known for the Orion Veil, but it is quite uncertain and must be estimated rather qualitatively for other H plus regions. In any case, let's take a look at how we can deal with this. Q of H can be estimated from the radio frequency flux and the distance. Basically, Q of H is related to the radio frequency free continuum luminosity. So it's easy to set up a simple relationship between Q of H and the distance between us and the H2 region and the radio frequency flux, which is easy to measure and which has been measured in many cases. So all this works pretty well. And therefore, we can calculate for these other 7 H plus regions, we can calculate the expected equilibrium field in the PDR if, in fact, the PDR is magnetically dominated and the magnetic field pressure is resisting the pressure of the stellar radiation and the hot gas. Although in this case, actually, I've left out the contribution of the hot gas because in most cases we don't know too much about it. So I used that equation, the Troland equation as is now known. I used it, I took an electron temperature 7,000 Kelvin. That's not very sensitive to the electron temperature. I assumed the ratio of far UV to EUV flux is 2, and I assumed no contribution from PX other than in the case of Orion, where we know quite well what the contribution might be. So let's see how it comes out. Here is now a list. Here is a list of all 9 galactic H plus regions for which this VLA Zeeman technique has been applied. So for all 9 of these H2 regions, we know something about at least the line of sight magnetic field in the PDRs that lie in front of the regions, because remember, the technique only operates in absorption lines in this particular case, so we only can measure magnetic fields in PDRs that lie in front of the H2 regions. So here you see a list of some fairly commonly known and well-studied galactic H2 regions, some references just for the record. Distances and fluxes taken from the literature at various frequencies. It doesn't really matter much what frequency you choose. And so fairly recently, actually, I sat down and just did some calculations. I used the Ferlin equation to calculate the equilibrium field to compare that with the fields that are measured in H2 region vicinities, in the PDRs in front of H2 regions via the radio frequency Zeeman effect using the VLA. And so here's what I learned. You see here the same list of H plus regions on the left that you saw on the last table. This column represents the radial distance between the ionizing stars and the illuminated face of each H plus region that I estimated by looking at the radio continuum maps to get a sense of the scale of each H plus region. This number RIF, as I say, is rather qualitative. It's very difficult, especially in H2 regions that have complicated structure, to know just what number to choose. But I chose, independently of any calculation of BEQ, I chose a value that I thought was reasonable. I calculated Q of H from the measured radio fluxes and distances. And then these are the numbers. It's shown in green here are the numbers calculated by the equation. And then shown in yellow are the magnetic field strengths that actually have been measured over the years via the Zeeman effect, the line of sight component, that is to say. And keep in mind that the line of sight, oops, whoa, that's not what I meant to do. Let me go back. Let me go forward. Okay, there we go, wrong button. Keep in mind that the line of sight fields that we measure are lower limits on the total field strength, because obviously the field could be nearly in the plane of the sky in principle, in which case the line of sight component would be small compared to the total field strength. But on the average, the line of sight component should be fairly comparable to the total field strength. So if you compare these numbers, if you look at the numbers here calculated from the formula, and you compare them with the numbers that are actually measured, it turns out in every single case that we know of so far, the magnetic fields actually measured in the PDRs in front of these H plus regions are comparable to the magnetic fields that you would expect using this simple magnetic equilibrium model that Gary first thought about and that was published in 2007 by Pellegrini et al. I have only 5 minutes left, but I have actually less than 5 minutes to say. How about that? That's tremendous. I'm sure you'll be happy. That's a good thing. Thanks, Bob. So what do we make of this? Well, the fact is that all 9 H2 regions for which we have measured values of magnetic field strengths in their PDRs, in all cases, the measured values of the line of sight field strength from the Zeeman effect are very comparable to the magnetic fields that you would expect given this magnetic equilibrium that I've described. That suggests that the physics of PDRs probably can't be well understood without taking into consideration the magnetic field. It may play a crucial role. It may dominate the pressure inside PDRs. And if so, then magnetically supported PDRs are likely to be much less dense and much larger in extent than you otherwise would expect in the absence of the magnetic field. This result may not only have implications for magnetic fields in PDRs in sort of standard H2 regions in our galaxy, but also much more luminous H2 regions in, for example, extragalactic starbursts. So the magnetic field is important. I end with this concept here. Magnetic modeler, PDR modelers, beware, because if you ignore the magnetic field, you're creating a problem. Do not let that happen to you. As Nick Abel said, I keep making that mistake. It's hardwired into my brain. As Nick Abel said earlier, make magnetic fields great again. I will do that. Believe me, just so you understand, I'm not a very good Donald Trump impersonator, but anyway, and I shouldn't mention that name in these places. But anyway, the magnetic field is apparently fairly important. A plausible case can be made that any model of PDRs that excludes the effect of the magnetic fields is probably seriously at risk for misrepresenting the physical properties in those PDRs. So thank you very much.
Yes, you. Microphone here, please. It's wise to wait for it.
So if there's time, I actually have 2 points I'd like to make. One is that so every scenario where you can apply this technique, as you say, you have to have the PDR sort of along the line of sight.
Yes.
So unfortunately, we can't actually determine the width any other way. So it'd be really nice if it was possible to compare side by side a model with the magnetic field effect and without, and see if there's any sort of chemical or other observational way of distinguishing some kind of prediction from the models of what we might see if the magnetic field is really causing this alternative distribution of matter. And then the other quick point is that you accounted for the dynamical effect of the magnetic field in these models, but actually, in some scenarios at least, I think, magnetic fields can also affect the PDR chemistry in itself by, for example, excluding cosmic rays, maybe reducing or increasing the cosmic ray ionization rate. So it'd be interesting to see what... I assume that wasn't included in the cloudy model, but it'd be interesting to see if how this would...
Cosmic rays were included in the cloudy model.
Yeah, but not necessarily the effect that the magnetic fields have on the cosmic rays, which could be to reduce their amount or increase them, perhaps.
Well, you might imagine if the field is compressed, you might imagine it would bring the cosmic rays in, and the cosmic ray density would be much higher. So, in fact, that idea was explored in this paper. It didn't make a big difference.
Okay.
It may just be an effect of the of needing a different geometry. But have you any comment on the fact that at least for a plane geometry, the line of sight magnetic pressure is the component that actually has no dynamical effect?
Sorry, I didn't quite understand the question about geometry.
So So if you look at the MHD equations, the line of sight magnetic field has no dynamical effect. So it seems strange that it's balanced against the pressure. I guess it may be something to do with the geometry or something where we have to be a bit more. But you know, it's the line of sight magnetic field will just thread the whole thing, and there is no pressure balance due to the stress tensor you get from magnetic fields.
Well, I don't know what exactly is happening, but all I can say is that what nature tells us is that in these cases, at least, a plausible case can be made that the actual measured field strength is enough to provide this balance. And whether that's truly the most important physical principle going on or not is unclear. It's of interest to know that in every single case, as I said, the magnetic field is strong enough to provide just that balance. I'm not sure if I totally understood your question or totally answered your question. We can talk later.
So you go one slide before in your presentation, the one that you got the table with the.
Oh, yes. Let me go back.
Yeah, that one. So in NGC 6334A, the magnetic field from H1 is 50. The magnetic field from OH is 500.
That's right.
Why is that?
Sharp eye. I was hoping you wouldn't see that. That's fine. Young people have good eyesight, and they often see things that older people hope they'll ignore. Well, each of these cases is different. Each is a different type of geometry. NGC 6334A, the H2 region is a shell, and the OH measures magnetic fields right in the vicinity of the shell, and the H1 I think is measuring magnetic fields that are in a lower density region that are probably not as closely related to the PDR itself. So I believe that and the geometry of NGC 6334A suggests that the OH measurement of the field is the one that's more relevant to this story than the H1, which, as I say, I think in the latter case, H1 measures magnetic fields in a lower density region more removed from the from the stars.
The last question for Tom will come from Chris.
Okay.
You're not going to go and give a tantrum, I hope. No tantrums. Okay.
Just history, which is even worse.
Oh, okay.
What was I going to say? Oh, yes. Here's a point that's so subtle it's probably unattainable, but
I'm
listening to your talk, I was sitting here thinking how Spitzer or Tommy Gold would have thought 50 years ago, and they would have said, yeah, your magnetic field balance, yes, absolutely, of course. What else could it do? But then they would have said, suppose you think about that gas before the magnetic field starts being compressed. How is it related at that time? You know, you could trace it back to the dynamo business or maybe the equipartition business or whatever was happening to generate the magnetic field before it got compressed. So is there any conceivability of tracing the parameters back so you'd have a relation between thermal pressure, density, magnetic turbulence, et cetera, et cetera, et cetera? It's a sort of a missing link in your argument. Actually, that's not quite true. It precedes the logic and your reasoning.
Well, we can, in many cases, and certainly in the case of the veil, we can, as Nick pointed out, we can determine what the different energy components are currently, the magnetic energy density, the turbulent energy density, thermal energy density, all the energy densities can be estimated in some cases, and the veil is a good example of that.
Before it got compressed.
No, we don't know. No,
that's what I mean.
I see. No, we
in general, there has to be a reason for the strength of the original magnetic field that got compressed has got to be related to some physics. And so the question is trying to figure out a way to trace it back before the conditions that you can measure.
I don't think we can do that, nor, in fact, do we, of course, understand the ultimate origins of magnetic fields. Right. People, sometimes physicists say to me, if I give a talk to a physics group, they say, well, what's the origin of the magnetic field? I tell them I don't know. If they look at me as if there's something wrong with me, I say, well, biologists studied life forms today, but if you ask them what's the origin of life, they don't know either. So the question of origins of magnetic fields is a very different question, which is very much not understood today, certainly not understood by me.
I'm afraid that we have to move on. Thanks very much, Tom. We'll seek with great efficiency into the next speaker, John Beckman from the IAC.
Correct.
And the floor is yours.
Thank you. Well, first of all, it's more than a routine thanks to the organizers for inviting me here. I'm very grateful because it's a very fine atmosphere. It's been a wonderful meeting, and I've learned a lot, and you'll see in a minute why I've learned a lot when you see how little I actually know. The other thing I'd like to put in is a nostalgic note, because one of the pleasures of being here is to coincide with David Lambert. We first coincided in 1962, and he actually helped me more than any other single person, well, equal with David Petford, as he himself pointed out, with my thesis. He wasn't my supervisor, but he gave me the physics for my thesis. So that's one piece of nostalgia. And another piece of nostalgia is that in 1965, I had the equal pleasure of meeting the Pineberts in Berkeley when they were graduate students, and I was a very, very young postdoc at Lick. And so these are very ancient memories, and I'll pass over them, but just to say that I still remember with warmth the meeting, and it's even warmer as I am today. So I'll go straight on, and I'll talk about BUBBLY. Now, the only link that BUBBLY has with cloudy is the name. It just sounds right because cloudy sounds right, and that's the only reason we called it BUBBLY, because cloudy has such a lot of citations, and you never know, if you give it a name like that, maybe we'll also get some citations. But I will also give a little bit of publicity to the instrument that we're using for making the measurements I'll describe. It's called GAFAS, Galaxy H Alpha Fabry-Perot Spectrometer. It's a permanently available visitor instrument on the 4.2-meter Herschel telescope on La Palma, and it's available as a visitor instrument, and if anybody, as a result of this talk, has any inclination to use it, you can talk to me. And of course, gafas, for those of you who are not Spanish-speaking, means spectacles. So, okay, so I'll first talk about observational evidence for expanding ionized shells in H2 regions, dating back to work done by my graduate student Monica Relaño, who, as a matter of fact, also had the pleasure of working with Manuel Peinbert on NGC 346. So it all links together, everything links together. But in this case, she detected expanding shells using an older Fabry-Perot in external galaxies. Her project was to look at a series of nearby external galaxies, and with the instrument we were obtaining the luminosities in H-alpha of each of the H2 regions that we defined, and also their kinematic parameters, namely their velocity with respect to ourselves, and also the velocity dispersion. So we had these moment maps and the observations. This is the intensity map. And what Monica detected was a series of, this is a pair of spectra of individual H2 regions. These are complete H2 regions. They're extragalactic, so then we only had the resolution on one region at a time. So each of these profiles represents one region. The central peak we interpret as coming from the bulk of the turbulent H2 region, while the side peaks are due to ionized gas in expansion, with velocities in the range 40 to 90 in this case, kilometers per second. So we could use the measured parameters to calculate the kinetic energies of the shells. Well, this is just a scheme to show what we were observing. The big peak in the middle is the basic turbulent emission from the H2 region, and the side peaks are the shells, which are weaker and expanding symmetrically. So, not necessarily being able to read all the lines, I'll just pick out a few points. First of all, these are big. These are radii of 80 parsecs. So these are big H2 regions. Obviously, there's a pure selection effect. You're looking out at external galaxies. You can't see the small H2 regions. And these are their H-alpha luminosities. The velocities, then we made an estimate of the electron densities in the shells using H-alpha, so we could make an estimate of the masses of the shells. We also used to get the energy balance, we used an equivalent number of O3 stars. We could have used an equivalent number of O7 stars. And so this gives the kinetic energy in the shell, the kinetic energies of the winds that the stars put out, and the total radiative energies. You can see these two are both in terms of 10 to the 51 ergs, so they match each other. And what we found was that in this set of data for these galaxies, it was sufficient for the wind energy was sufficient to give the shell momenta and the shell energies. We could therefore ignore the supernovae, and in fact, the ages of the shells you could work out from their expansion parameters were such that, in general, we would not have expected that supernovae had yet gone off in the H2 regions in general. So that was older data, and it was the basis of the work. Now, one thing about these shells, I mean, we were challenged all the time by the instrumentalists to say that these wings that we could see in the profiles were real. they would say that now there were instrumental effects. I mean, it's actually impossible to have got these from instrumental effects. But at one time, the wings in Spanish are alas, and Monica began to get depressed by all these attacks on the data. So at one stage, when she was just about flaking out, I gave her a can of Red Bull, and in Spain the advert for Red Bull was Red Bull te da alas, gives you wings, and somehow or other this seemed to work, and eventually her work was revindicated. So BUBBLY is a program that was written by another of my students, Artemi Camps, which is to systematically search for and detect bubbles. And so it's we use it. The basis of it really is something fairly simple, that you can detect peaks in a set of multiple Gaussians using the second derivative. Basically, it's that. And so we apply it, and this is an example of a single pixel, the emission of a single pixel with a big emission from the H2 region, a pair of emission peaks, and some other peaks. Now, what BUBBLY does, you map the galaxy and its H-alpha emission in this way with a velocity resolution typically of about 8 kilometers per second theoretical, and in practice you can get better than that. And you map the whole thing, and then you put in a series of conditionals to reject peaks which are equally spaced but not sufficiently equally spaced within the limits of the resolution of the instrument. And you make what we call an expansion map. And this is an expansion map of a superbubble. This shows the highest velocity in the center, 130 kilometers per second in the center. And this is projected along the line of sight, of course, so we can see that we can map. These are in the antennae. This is an expansion map. These are not intensities. These are velocities of separation of the peaks. That's what these maps are. And indeed, here, as an illustration, we found on the antennae a double bubble, thereby, well, I'll go into that a bit later. And this is a map of the superbubbles detected in the antennae. The colored diagram is the expansion map, and the contours are H-alpha isophotes in intensity, showing that the centers of the isophotes are the centers of the expansion maps, and that therefore these bubbles are centered on the stars producing the H2 region. And this is obviously the antenna is the nearest LERG, so it's the nearest high energy object to look at, and we found these bonzing great superbubbles. And just look at the radii of these superbubbles. This is a 546 parsecs, so nothing of these piddling little Orion nebulae. This is real stuff. Now, obviously, I'll withdraw that completely. I will now reverse that deprecatory remark. I always complain about high redshift people because they can't learn any physics, really, because they haven't got good enough data to know anything. And I think I'm in the same position with respect to the Orion Nebula. With the Orion Nebula, you really know. With these, you get what you can. But nevertheless, we are able to do some quite useful work. And so, of course, these things are very big. They are belong to giant H2 regions. It's interesting that I've never felt comfortable with the term giant H2 region because, you know, what does it mean? What's a giant region? But in a recent paper, Javi Zaragoza was able to make a physical distinction between giant H2 regions and smaller H2 regions. This physical distinction is based on the fact that the large regions are gravitationally bound and the smaller regions are pressure bounded. And you can work this out using virial equilibrium or in general, but in any case, the H2 regions below this mass limit have a density which, the mean density, which you can measure using the electron density, reduces with increasing radius. But when you get to this limit, it starts to rise. This is a clear indication of that the reason that it reduces below the limit is because the regions are getting bigger with respect to the scale height of the disk. And the reason why the density goes up into the giant H2 regions is just that you're getting gravitationally bound. And so that is no longer the key point. And not only is this true of H2 regions, it is also true of the molecular clouds from which they arise. So that I think that one of the things that we know is that giant H2 regions are very massive, more than 10 to the 6.5 solar masses, and are gravitationally bound. Now, in this case, we can measure the mass in the shells, the kinetic energy in the shells, and an age estimate, which is an expansion age. We're talking about a few mega years here. We can estimate this using Mickey Mouse terms, that is to say, just dividing the size by the velocity. And then we can do it slightly better using models, but I'm not at all sure it is much better. But then we can compare it with photometric spectroscopic age that we didn't determine, but were determined by people using Cloudy. So at last, I am able to actually relate my work to Cloudy in this context. Here is a comparison of some of the detected bubbles with high-resolution H-alpha images in the Hubble. So you can see that the geometrical detection of a bubble does match reasonably well the expansion detection of a bubble, but in fact, the expansion method is more selective, and actually you detect more bubbles and detect them more precisely using velocity tagging than just by looking at the morphology. Well, doing diagnostic diagrams for the shells in the antennae, that they all fall within the ranges occupied by the H2 regions in the diagram. This is just H-alpha over nitrogen 2 versus H-alpha over sulfur 2. Simple diagram, but it does say that these large shells are older and more relaxed shells than those occupied by smaller H2 regions, which I'll come on to. And this diagram puts them all in the in the H2 region range. Okay, so we've done some attempts to make hydrodynamic simulations. The density of the shell is related to the scale gas, and we've made some comparisons, and we've tried to improve our estimates of the ages using these simple hydrodynamical simulations. Here is a set of bubbles detected in M83. It's not an interacting galaxy. It's a local standard star-forming galaxy. The shells are smaller, less energetic. We're talking about shells of only 100 parsecs radius with lower kinetic energies and ages of just around a megayear in the cases of all these detected shells. We've now surveyed a number of local galaxies and are beginning to form catalogues of these bubbles. But our next, I talk about one specific bubble, which I want to talk about because it's a detailed piece of work, and it's of interest. We're not as nearby as local H2 regions, certainly not as the Orion Nebula, but we are in M33, a local group galaxy. We can resolve quite well many aspects of the objects that we're looking at. So as a result, on a particular region, whose H alpha emission map is given here. The region itself that I'm going to talk about is this intense blob. And these are the profiles of a given pixel. This is the profile from our GAFAS image, GAFAS cube, where we see that the central peak and 3 successive shells. We repeat it when we obtained this. In order to do diagnostics, we obtained data using slit spectra, and we could find, for example, in this for the nitrogen 2 line, we find the same shells with the same relative intensities. The blue shifted wing is brighter in general than the red shifted wing because it's coming towards us. It hasn't got so much dust between us and it. So the expansion maps, this is the expansion map made from the slowest shell, the inner shell. This is the expansion map which we made using the second shell. This is the third shell. You can see that the bigger the shell, the slower the velocity, the lower the velocity, which is what you'd expect. And so we are claiming that we have found 3 supernova shells around a young star cluster in M33. It's just been accepted in monthly notices. Now, so the diagnostic diagram for each of the shells, this is it's not exactly a BPT diagram, shows that the diagnostics, there's more than one, puts them in the supernova range, whereas the central peak lies in the H2 region range. These are the radii of the bubbles, so that the smallest one and the fastest one is at 12 parsecs. So we're talking about smaller, less powerful expanding shells. The velocities are, however, between 50 and 100. We can work out the mass in the shell. The biggest shell has a minimum mass of 300 solar masses, and the other shells have 150 solar masses respectively. We can work out the various physical parameters and an age, and the ages are, for the most recent fastest shell, 20 kilo years. These are not mega years anymore. These are very recent events, 40 and 114 kilo years. Now, the question is, so we believe that we have detected 3 concentric expanding supernova shells. So here are the summary of the key parameters. It's basically the same as before. It's clearer, but I won't dwell on it. Because so we looked in the literature to see if there was correlating evidence. One was radio detection of a supernova remnant, and indeed it's the brightest radio continuum detection of any region in M33 apart from NGC 604. So it is very bright as a radio source. There's a detection of a molecular cloud associated with the H2 region, which I'll talk about. And the age of the stellar cluster has been measured, and it's between 6 to 12 mega years. And the progenitor star masses we can estimate as well are just under 20 solar masses. There are 51 OB stars in the cluster still, so the fact that 3 stars have gone off almost simultaneously is not totally ruled out. In fact, it's not ruled out. Of course, you might say it's very strange to find 3 supernova going off in the same simultaneously, but of course simultaneously with intervals of 10,000 years. So it is simultaneously in terms of stellar mass, but still, it's not at all ruled out. So there's an apparently severe problem with the scenario of the triple bubble, and that is that if you assume that the supernova sweeps out all the mass, obviously these masses, a few hundred solar masses and so on, they're clearly not the mass of not the stellar mass. It's swept up gas mass. Okay, this is clear. But if you assume that the supernova sweeps out the gas from the from the inner zone, first carved out by the winds and then swept out by the supernova. So that's okay for the first shell, but where does the second shell get its mass from? Where does the third shell get its mass from? So the answer is mass loading in an inhomogeneous medium. This work has been looked at in detail by John Dyson and his students and colleagues. So we were able to go to their work and borrow, because obviously we didn't do the modeling, but we could borrow, and we made... So actually, one of the points here is that we're used to clumpy, inhomogeneous media, and indeed, one of my students, Gianmanco, whose work was referred to yesterday by Gracina, wrote a program to a radiative transfer in an inhomogeneous clumpy medium, which we called clumpy, and it called cloudy as it used cloudy as a part of itself. But so we're used to the clumpiness of the medium, and the contrast between the clump densities and the ambient density maybe is 100 to 1,000, or even more, in fact. So we can do some quick work. We can process which we can operate to transfer mass from the dense clumps into the surrounding medium. We used various different types of flow hydrodynamic ablation, photoevaporation, and thermal evaporation, slow wind and fast wind, and we made some basic estimates. And so we worked out, on average, for a 1 parsec diameter cold cloud at 10 parsecs from the center of the cluster, we'd get about 1 solar mass per, in 10 to the 4th years. So we can, it's quite plausible under this hypothesis to get the masses that we observe into the inner shells, because what you're seeing is that the dense clumps are being evaporated away. They still stay there, and in fact, even after these 3 supernovae have exploded, a major fraction of the denser clumps are still there. So it's not ruled out. Now, the interesting thing about this is that it enables us to, and it will enable us when we look at it in more detail, to study the theme of stellar feedback, supernova-based stellar feedback in general, because it's a unique opportunity to look at stellar feedback because it enables us to explore dynamically the clumpy nature of the medium. So I hope I've tried to explain that it's true that line ratios and spectroscopy and photometry are absolutely important for the study of H2 regions, but kinematics, the kinematic element, is extremely important too, and should not be neglected. So this is a summary, and this is a summary. And thanks.
Thank you, John. Are there questions on this talk?
Yes.
Gary.
A question, not a question, but a very minor comment. You talked about where several names came from. Cloudy actually was not named after things in the sky. It was named after the East Anglian weather.
Good.
Will?
Okay. So, just a comment that might be helpful for your analysis of that very interesting triple supernova shell. Maybe you should look at simulations done by, I think it's Gritschneider, have done simulations of supernova remnants going into highly structured molecular clouds and finding that it doesn't, in fact, destroy the whole cloud. It just goes through the low density parts. So they might.
Thanks. I'll ask for the reference. Okay. Thanks.
I would like to point out what we heard before, that the bus for the museum will leave out in the usual place, the parking lot, at 1:30, not any other time. It will be at 1:30. And thanks to John and all the other speakers of this marvelous session.
I can't see myself to unhook it. Oh, yeah.